Good morning, class. This is the fourth chapter, force system resultants, or reduction of a system of forces and couples. Objectives. Students will be able A. Reduce a system of forces and couples to a simple system with a force and a couple. B. Resultants for certain special force systems. Introduction. When a rigid body is subjected to a system of forces and couples, it is basic task to reduce the complicated system to an equivalent simple system with the same external effects on the body. There are two diagrams. So for given a complicated force system, how can we reduce it into a very simple system with just only one force and one couple moment? This is what we will explore in this section. How to do this? Before make reduction, we should review some contents we've already learned, called moving a force off its line of action. This is a theorem of translation of line of action of a force, which tells us that a force can be translated acting through another point added by an additional couple. For example, originally the force is applied at the right end. Now we try to translate the force act at the point O. We must add an additional couple with the moment, which is equal to m equals to Fd, which is just the force act at the original place, its moment about O. General case. In a three-dimensional case, a force acted at A can be translated, acted through point O, added by an additional couple with the moment m equals to r cross f. So this is a three-dimensional case. Now let's make reduction of a force system. 4.8. Reduction of a forces and couples system. Begin with a force system as shown in figure A. Arbitrarily select a point O. Translate each force to O plus corresponding additional couple, shown in figure B. Then we get an equivalent force system. The additional couple is with the vector as follows. M1 equals to R1 cross F1. M2 equals to R2 cross F2. Those are two vectors to represent the additional couple. Here, MC in the figure is an original couple, and which can be translated to O freely, because couple moment is a free vector. The system in figure B can then be considered as the combination of two simple systems. One is a concurrent force system, the other is system of couples. Then we find the resultants for both simple systems, respectively. For the concurrent force system, we get the resultant Fr, which is equal to the summation of all forces, vector summation. And for the couple systems, we can get the resultant, which is MRO. It is equal to the summation, vector summation of all the additional couple moments and the original couple moment, MC. So this is the intermediate result for reduction of original force system. So finally, the force system can be reduced to a force acting on O and a couple, as shown in figure B, which can be represented by following vectors respectively. Fr equals to sigma F, MRO equals to MC plus sigma MO. For the convenience, the two vectors are defined as the principal vector of given system and the principal moment of the system about O, respectively. From the process of reduction of the forces system, it is shown that the principal vector Fr are independent of the location of O. But the principal moment about O, MRO, depends on O because R1 and R2 were used in computing M1 and M2. Use this formula. So the principal moment will be dependent on the selection of point O. Now this is a conclusion. Generally, a system of forces and couples acting on a body can be reduced to a force acting on O and a couple, the vectors of which can be presented by principal vector and the principal moment, respectively. These are expression of principal vector and the principal moment. So the conclusion, in one word, we can use this diagram to show the reduction result. Any complicated force system can be reduced into one force and one couple. They can be represented by vector, principal vector and the principal moment. Okay, this is a general case for any three-dimensional case. Now, let's come to some special case. Reduction of special forces and a couple system. The first special case is concurrent force system. That means all the forces act across the same point. All forces act across point P. This can be either three-dimensional case or two-dimensional case. There is no couple moment originally. There is no couple moment. So for this case, the resultant is just a force act on P, which is equal to the sigma F. That means the vector summation of all the forces. So the result is very simple. For concurrent force system, we get a resultant force. So we call this one force resultant force. Second special case 2, coplanar force system. That means all the forces lie on the same plane, as shown in the figure. The left one. There are forces and couples. All the couples are act on this plane. All the forces are also act on this plane. So we call coplanar force system. According to the process of reduction, each force is moved to a point O, arbitrarily selected, added by additional couple correspondingly. Then we make resultant respectively for the two kinds of forces system, simple system. So resultant is a force. Fr equals to sigma F. And a couple with moment MRO equals to sigma M plus sigma R cross F. And because all couples align on the plane, so the resultant couple were oriented vertical to this plane. That is, MRO is perpendicular to FR. So at the right, in diagram right one, we get the result is a force acted through O with a couple. The moment is given by sigma M plus sigma R cross F. Now, can we make further reduction of this case? Fr can be repositioned at a distance d from O, as shown in figure C. Can we do this? The answer is yes. We just make further translate of the action line of Fr to act through another point with a distance d. D can be determined by MRO divided by Fr, or in other form, FRD is equal to MRO. When there is no original couples, this relation becomes the resultant moment theorem. That is, the moment of resultant force Fr about O is equal to the summation of the moment of each forces. So this is called the resultant moment theorem for the general planar force system. So this is a byproduct of this force reduction process. The third case, reduction of coplanar parallel force system. In the diagram, we can see there are three parallel forces act at the point with a distance d1, d2, d3. Now, first we can reduce this force system to the left point, left end, that is a grip point. So we first reduce the force system to grip point at the left end. So the result is the resultant principal vector is Fr, which is equal to F1 plus F2 plus F3. And the principal moment, which is F1 times d plus F2 times d2 plus F3 times d3. So this is the initial reduction, which is acted through the left ends. The result Fr is acted at the left end. Now, according to the further reduction in the last case, we can make further reduction. That means we can determine a point where the Fr resultant force acted without any couple moment. So make further reduction to resultant force to a resultant force to get to the position where Fr acts. So just apply the theorem of moment, resultant moment theorem. We've just discussed. Applying resultant moment theorem, we can calculate the moment of resultant force about the left point, the left end, which is FRD, which is equal to the moments of all the forces about the same point. So, which is equal to F1 times D1 plus F2 times D2 plus F3 times D3. Finally, we can determine the D. D is the bracket divided by Fr. So now, the resultant force acted at another point with a distance from the left point, the left end. So this is the third special case. Now let's do an example. 4.15. This is a coplanar system case. Replace the forces and a couple moment system by an equivalent force and couple moment acting at point P. That means give you a point P. Please reduce this given system to P. According to the process we've already discussed for the general force system. We can solve for this problem. This is a plan. Because this is a coplanar force system, we can use the Cartesian component to represent the principal vector and the principal moment. Use these two formula. The principal vector and the principal moment can be obtained. Now, solution. Use the vector, the Cartesian vector component. The Fr can be represented by its two projection onto x and onto y, respectively. So first we calculate the projection of Fr onto x-axis, which is equal to sigma Fx. So we make summation of all the projection of original forces onto the x-axis. Then we finally get Frx is equal to 51.996 Newton towards the left. Likewise, we calculate the projection of Fr onto y-axis, which is equal to the sigma Fy. That means the summation of all the projection of forces onto y-axis. Finally, we get Fry equals to 170 Newton downwards. These are two projections. Finally, we can make the resultant of the magnitude of a resultant force, principal vector. The magnitude is equal to the square root of the squared projections of two directions. Finally, the magnitude of principal vector is 178 Newton at the angle, a direction angle, theta, which is equal to arctangential, Fry over Fyx. Finally, which is equal to 73 degrees. Now, we finally get the principal vector with the magnitude and the direction angle. Then we compute the principal moment. Principal moment is also a summation because this is a planar problem. So we can use the scalar summation of moments of all the forces about point P. In calculation of the moments of this force with 60 Newton, we used the analytical method. That means we first resolve the second force into x component and y component, then calculate the moment of these two components about point P. We'll make this calculation easier. Okay. So here we can see there are 60 times cosine 30 degree times 8 and 60 sine 30 degree times 12 minus 8. So there are two components. Finally, we get the magnitude of this principal moment is 2,676 Newton meter, which can be converted into 2.68 kN meter counterclockwise. So this is the final result of this problem. The force system can be reduced to a force of 178 Newton at a direction angle 33 degree acting at P, and a couple moment 2.68 kN meter acted on this plane. Okay, this is all of this class. This is homework.